In this video, I want to talk about the successive approximation register ADC. Okay, it's also called the SAR ADC, and the block diagram of the SAR ADC is shown on the screen. But we'll come back to this in a moment. I just want to talk about the background to this before we come back to this block diagram. I don't know, but if you have ever played the game of guess a number with a young kid. So the basic I used to play this a year or so back with my young kids. So the basic idea is that you choose a number between 0 and 1000 in your mind, and the other person has to guess what number is. And the best way of doing this guessing, so let's say the range that you decide is between 0 and 1000. Okay, and you have chosen a number and I don't know what the number is. So the best way to get the number would be to say, okay, is the number greater than 500? If the person says no, then I know that the number lies in this interval, right? And then I say, is the number greater than 250? If the person says yes, I know that the number lies in this interval. Otherwise, the number lies in the interval from 0 to 250. So let's assume that he says yes, and the number lies between 250 to 500. Then I say, okay, what about comparing the number with 375? And let's say the person says that the number is below 375, then we know that the number lies between 250 to 375. And what you can do is at each stage you can narrow down the interval in which the number lies till you know the number itself. Okay, so what we are doing is basically successively we are approximating the number that is in the other person's mind. So in the first stage, we reduced so we knew that the number was between 0 and 1000. And in the first stage, we reduced the range of the numbers to being between 0 and 500. So there are 500 numbers now. In the next stage, we reduced and said that we have 500 values, 250 values from which we have to choose the number. In the next stage, we said we have only 125 values. In the next stage, you will have something around 62 values to choose from, and so on and so forth. At every stage, we are reducing the interval till we reach the exact number itself. And this is the idea that we use in successive approximation register ADC as well. So imagine you have an ADC. The range of the ADC is 0 to 5 volts. Okay, so what the ADC wants to do is it wants to divide the 0 to 5 volts into some intervals and denote each interval with a digital value. So let's assume that we are doing a 8-bit conversion. So we want to divide 0 to 5 volts into, a 3-bit division, a 3-bit conversion, and that means that there are 8 levels. So we want to divide 0 to 5 volts into 8 intervals. Okay, so that's 4 and that's 8 levels. And what we want to do is we want to denote each interval with a digital number. So 000, 001, 010, 011, 100, 101, 110, and 111. So what we want to do is we want to find out if we have an analog input, we want to find out where on this diagram does the analog value lie. So let's say the analog value lies somewhere here. Then what we want to do is we want to denote that analog value by this digital number. Okay, so that's the process of analog to digital conversion. Now, how does successive approximation register do this? So what it does is, in the first step, it compares this analog value with the middle value of the range. So with, let's say, 2.5 volts. Okay, and then we find out that our analog value is smaller than 2.5 volts. And once we know that, what we want to do is we want to compare it with 1.25 volts. And then we find out that the voltage is, the analog value is greater than 1.25 volts. So now we know that the analog value lies between 1.25 and 2.5 volts. So the next, what we do is we compare it with 1.875 volts. And we find out that the value is smaller than that. And therefore, we know that the analog value must lie in this interval. And therefore, the digital output corresponding to it has to be 0, 1, 0. Does that make sense? So what we have done is, at each stage, we are trying to approximate the analog value. So we are saying in the first stage, we said it is between 0 to 2.5 volts. In the second stage, we said, so that's the first stage. The second stage, we said it was between 1.25 to 2.5 volts. And then in the third stage, we said it was between 1.25 and 1.875. And so we have got to the granularity that we wanted, and so we stop. So having understood this, I think we are in a place where we can now look at the block diagram of the SAR ADC and try to understand it. So here's the block diagram of the SAR ADC, and I've just drawn the 0 to 5 volt range here along with the digital numbers that correspond to each of these intervals. And let's just look at this conversion for a 3-bit conversion. Okay, so we have 8 levels. Okay, and let's assume that the ADC value lies here like we assumed in the previous case. So how does this block diagram work now? So we have an analog input, and the analog input is given to a sample and hold amplifier, and the sample and hold amplifier holds this analog value at this point. And this analog value is now compared to the output of a DAC. Okay, and the output of the DAC, of course, depends on the input of the DAC, which is controlled by the control logic. Okay, so if the range of numbers that we have, the values, analog values that we have is from 0 to 5 volts, and we are doing a 8-bit conversion, then what the control logic does is it gives us the first number that it gives as an output is the middle value of that conversion. So let's say the middle value is this one, okay, 0, 1, 1, 1. So the first value that is outputted by the control logic is 0, 1, 1. And the DAC, as a result of this input, gives us 2.5 volts. Okay, so it gives us 2.5 volts. So what the comparator then does is it compares our analog value, which is here, with 2.5 volts, and it tells us that the analog value is smaller than 2.5 volts. And because it is smaller, the control logic then generates the value 001, because that's in the middle from 0 to 2.5 volts. And the output of the DAC corresponding to that is going to be 1.25 volts. So then the comparator compares our analog value, which is here, with 1.25 volts. And the output then is, the output of the comparator tells the control logic that our analog value is greater than 1.25 volts. Because it is greater than 1.25 volts, the control logic then generates the value 0, 1, 0, which the DAC uses to produce 1.875 volts. The comparator then compares 1.875 volts with the analog value and finds that it is lower than 1.875. Okay, so look at the conversion then. The first number that we got was 0, right? Because your analog value was less than 0, 2.5 volts. So let me write this as V analog. It was less than 2.5 volts. So we got a 0 as our first bit. Then V analog was greater than 1.25 volts. So we got a 1. And then V analog was less than 1.875 volts. So we got a 0. So our digital number is 0, 1, 0. So this is the digital number corresponding to the analog voltage that we started out with. Okay, so that's how a successive approximation ADC works. Of course, there are other components to this successive approximation register ADC, and the basic idea is that the approximation happens successively in time. So we need a timing circuit that kind of times when the 2.5 volt is generated and when the 1.25 is generated and so on. And what happens is it requires at least 3 clock cycles for us to do a 3-bit conversion. Hopefully that gives you an idea of what a successive approximation register ADC is and how it works.